Okay, so continuing with our linearization, we did something in the previous slide, of course, and in our previous presentation where we showed the linearized form of the Ricci tensor. This was what we obtained. This is plus some higher order from order 2 of H and so on, but that's what we obtained. Now we are looking at the Einstein field equations. The Einstein field equations can be written in this form, where G mu nu here is equal to that, with what we usually call the Einstein tensor, written in this form. Of course, if this is the case, therefore means from this equation that this is equal to that. I can try to contract these two indices all at the same time using G mu nu. So I multiply through the whole expression with G mu nu. On doing that, these two expressions, as usual, will give us 4. And of course, here we have G mu nu contracting mu nu here. Again, this gives us a scalar, but we'd like to denote it with some dummy index, lambda, lambda, sigma, sigma, whatever, just a dummy index to denote that this will eventually be the trace of our stress tensor. Here, having done that, this of course gives us the Ricci scalar. We have here this minus 4 divided by 2 gives us 2. Evaluating this, we obtain the Ricci scalar to be equal to that. So it's just a matter of taking this back into this expression here. If we do that, simply now reorganizing everything or rearranging gives us a second form of the Einstein field equation. So these two field equations are equivalent in every way possible. Okay, just in I have to say this because it's quite fair and just best I state that most of these derivations we'll be doing will be a la Weber, because I'm using most of the formalism are from his very wonderful book, Gravitational Principle and Cosmology. So looking again forward at this expression, so this one in particular will be most suitable for me, for my purpose now. Later on we may look at this, but for now let's look at that. On the right hand side, again, because we are linearizing this theory, first the metric tensor from our basic approximation. So from the right hand side here, I can write this to be equal to that, minus 8 pi g. Now in the bracket, I'm being careful to substitute this G mu nu to be eta sub mu nu plus H sub mu nu. I expand that, and this is what I have. I'm making a very desperate move. Well, but looking at this, we know that this G, the Newton constant, gravitational Newton constant, is a small value. Multiplying with this again, this very small value again, this whole term here can be very negligible, so I discard that. So I'm left with here on the right hand side, as far as the linearization goes, that this in essence is just equal to this alone. In other words, the whole expression is equal to minus 8 pi g, where z sub mu nu is equal to that. T sub mu nu minus half eta sub mu nu t sigma sigma. Now, if I were to substitute this again here, so in other words, everything we have done here is equal to that. If I were to substitute this on the right hand side and substitute the linearized form of the Ricci tensor on the left hand side, which is given by this, of course, the two will just cross over to multiply what is here on the left hand side, and I have here instead a minus 16, and the half here of course is gone. So this equation here is the linearized form of the Einstein field equations. So the Einstein field equation we had in two forms are these two, right? And their linearized form is this. So that is what we've just obtained. We're assuming that T mu nu here, as contained in Z sub mu nu, is of the lowest order in H sub mu nu, and that it is conserved. In other words, when I differentiate it with respect to S mu in this form, is equal to 0. First of all, let me try to perform some sort of contraction on mu and nu. By doing that, I'll try to raise mu all over the expression. Again, remembering that in this expression, since I'm raising or lowering any in this linearized theory, what I'm going to be using is eta. So I'm going to use eta mu rho z rho nu equal to eta mu rho t rho nu minus 1 all over 2 eta mu rho. Then this here is going to be rho nu, and then t sigma sigma. Yeah, this is what this gives us. At this point, I can write this whole expression as this. Z rho nu minus T this, and then plus half rho nu T sigma sigma equal to 0. And of course, I will say that this is not 0, so that in the end, Z rho nu is simply equal to T rho nu minus 1 over 2 eta rho nu T sigma sigma. Yeah, so this is what I've got. Now, I can decide at this point to contract Z and nu. If I did that, what I'll get is, for instance, let me make them both equal to sigma. If I contract them, this will be T sigma sigma minus 1 over 2 eta sigma sigma T sigma sigma. We knew, of course, that for G mu is equal to the number of dimensions. So, number of dimensions for 11-dimensional space, this will be equal to 11. But we're in 4-dimensional space. So, just as it applies for this, it also applies for this. This then will be equal to 4, since we're dealing with 4-dimensional space. Of course, it's the same thing we had when we talked about finding the, well, that may be a little bit different when you consider it in terms of how we came about that. But it's all the same thing because it's still the same contraction we did over there that we are doing here. Now, in this case, if I have this to be equal to 4, this gives me T sigma sigma minus, this is 2 sigma sigma, so this is minus T sigma sigma. So indeed, in this case, we have been able to show, I'm going to erase something here. I don't want to erase so much, so because of that, well, let me avoid erasing, just in case I may need one of these expressions. Z sigma sigma I've shown here to be that. Yes, by contracting Z and mu in this expression that we have obtained, let me put the mu somewhere else just so to be in line with that. Now that's what the contraction gives us. Now let's try to find the derivative. We've shown that this is equal to that, so I'll just put that somewhere up here. In other words, by raising mu, I obtain something like this: T rho nu minus 1 over 2 eta here. This is rho nu and T sigma sigma. Okay, we want to differentiate this, so we want to exploit this property here, the conservation of T mu nu, that the T mu nu, the X mu is equal to 0. In order to exploit this, we are going to say the Z rho nu, the X rho. Of course, you can see mu nu, so it's the same thing, rho nu, just to make sure it falls in line. In the end, I can of course decide, since it's the dummy index, change the rho to mu's. So this is again the T rho nu, the X rho, minus 1 over 2, this is a constant, this is rho, this is nu, the T sigma sigma, the X rho. We have been assured that this is 0 by this conservation law here. In the end, it therefore means that Z rho nu, comma rho, I can say is equal to minus half here, eta rho nu, T sigma sigma, comma rho. Now one more thing here, eta rho nu, I could decide to lower this by saying that this is the same thing as eta. Maybe I can say mu rho eta mu nu, right? Of course, if I were to evaluate these two, I'll obtain that. But then again, you can see we have shown that this again behaves or has the same property as the metric tensor, as we know, being a metric tensor, of course. So this might as well be the same thing as the conical delta rho nu. In other words, eta rho nu is the same thing as conical delta rho nu. So on that expression, it therefore means that I have here with me Z rho nu here, comma rho is equal to minus half conical delta rho nu T sigma sigma, comma rho, which of course this is minus 1 over 2. If I were to evaluate this conical delta, I'm going to have T sigma, sigma, comma, instead of rho, becomes nu. So at this point in time, this is what I get. Well, I can put that in sigma, I can put that as sigma, not sigma, please. This is Z. Z rho, nu, comma, rho is the same thing as minus some half of T sigma, sigma, comma, nu. We can be a little bit more elegant by saying that this is the same thing as 1 all over 2 minus T sigma, sigma, the whole of that, comma, that. Yeah, of course, because the minus just some constant, well, we can call that a constant, but it's a sign, not affected by this derivative. But then again, we remember what this was right from this expression. That minus T sigma, sigma is the same thing as Z sigma, sigma. So this is the same thing here as 1 all over 2 Z sigma, sigma, comma, nu. In other words, so maybe I can add one more relationship here. Z rho nu, comma, rho is the same thing as just half Z. This is sigma, sigma, comma, nu. By the way, since we are dealing with dummy indices, the dummy indices rho here on the left-hand side might as well also be sigma, sigma. And you can see that we have shown here 3 relationships. Well, these are just some relationships we shall need in trying to simplify this linearized form of the Einstein equations. We will, of course, hopefully try to perform the same expression also for the linearized form of the Ricci tensor. Hopefully that is what we'll be doing in the next presentation.